functions as power series. I can write 1 as 1 minus x plus x, minus x squared plus x squared, minus x cubed plus x cubed, and so on. If I group the first two terms, so 1 minus x minus x squared minus x cubed, and so on. By grouping the first two terms together, I'll put them in parentheses. From the next two terms, I can factor out an x. From the next two terms, I can factor out an x squared, and so on. Each of those terms has a common factor of 1 minus x. If I factor out 1 minus x, then if I divide by 1 minus x, I have 1 over 1 minus x is equal to the sum, as n goes from 0 to infinity, of x to the n, which is a power series. So find a power series for the function centered at c. F of x equals 1 over 1 minus 5x centered at c equals 0. So this is in the form 1 over 1 minus x. So I can rewrite this sum as f of x equals the sum as n goes from 0 to infinity of 5x to the n. This is a geometric series with r equal 5x, and it converges when the absolute value of r is strictly less than 1. So absolute value of 5x is less than 1. I can factor out a 5 and divide both sides by 5. So absolute value of x is less than 1/5. So 1/5 is the radius of convergence. If I expand this compound inequality, negative 1/5 is less than x, which is less than positive 1/5. And this would be the interval of convergence. F of x equals 3 divided by x minus 4 centered at 0. So I can rewrite this. My goal is to write it as a over 1 minus x, or 1 over 1 minus x. So 3 divided by negative 4 plus x. Then I'm going to divide each term by negative 4. So f of x is negative 3 over 4 divided by 1 minus x over 4. So I can rewrite this function as a series from 0 to infinity of a r to the n. So negative 3 over 4, r is x over 4 to the nth power. This series converges when r is less than 1. So absolute value of x is less than 4. 4 is the radius of convergence. And the interval of convergence is negative 4 to 4. Find a power series for f of x equals 4 divided by 5 minus x, centered at c is equal to -3. So I can rewrite the function as f of x equals 4 divided by 5 minus quantity x plus 3, and then I have to add 3 to balance out the denominator. So I'm forcing the center to be at -3. If I simplify the bottom, f of x equals 4 divided by 8 minus the quantity x plus 3. If I divide each term by 8, 4 over 8 is 1/2, divided by 8 over 8 is 1, minus x plus 3 divided by 8. So the first term, a1, is 1/2, and r is x plus 3 divided by 8. So a geometric series converges when r, absolute value of r, is less than 1, and it converges to a1 over 1 minus r. So this turns into the sum as n goes from 0 to infinity of a1, which is 1/2 r to the n, x plus 3 divided by 8 to the nth power. The series converges when absolute value of x plus 3 divided by 8 is less than 1. If I factor out a 1/8 and then multiply both sides by 8, absolute value of x plus 3 is less than 8. So 8 is the radius of convergence. If I expand this out, -8 is less than x plus 3, which is less than 8. If I solve for x, -11 is less than x, which is less than 5. And this would be the interval of convergence. Given 1 over 1 plus x equals 1 over 1 minus -x, which is equal to the sum, as n goes from 0 to infinity, of -x to the nth power. Which is equals to the sum as n goes from 0 to infinity of -1 to the n, x to the n. Find a power series for the function 2 divided by quantity x plus 1 cubed. And if you notice, this is the second derivative of 1 over 1 plus x. So if I want a power series for this function, 2 divided by x plus 1 cubed, which is the second derivative of 1 divided by 1 plus x. Which is the second derivative of the series from 0 to infinity of negative 1 to the n, x to the n. Now, negative 1 to the n is a constant multiple. If I differentiate x to the n, I have nx to the n minus 1. If I differentiate that again, I have n times n minus 1, x to the n minus 2. So the second derivative is the sum. I'm going to increase the index of summation to 2. You can keep it as 0, but the first two terms will zero out. Negative 1 to the n stays. The second derivative of x to the n is n minus 1, x to the n minus 2. So then, just so we don't have an x to the n minus 2, I'm going to change the index. If k is equal to n minus 2, then the series turns into the series from k is equal to 0 to infinity of negative 1 to the k plus 2 times k plus 2 times k plus 2 minus 1 x to the k plus 2 minus 2. And then I can simplify this sum as k goes from 0 to infinity, negative 1 to the k, negative 1 squared, k plus 2, k plus 1, x to the k. Which simplifies to be the sum as k goes from 0 to infinity, negative 1 to the k, k plus 2, k plus 1, times x to the k. Given that same power series, find a power series for the function arctangent of x centered at 0. So if f of x equals 1 over 1 plus x, let's compute f of x squared. F of x squared is 1 over 1 plus x squared, which is the series from 0 to infinity, negative 1 to the n, x squared to the n power. So notice that the integral of 1 over 1 plus x squared is equal to the arctangent of x. So 1 over 1 plus x squared is equal to the series from 0 to infinity, negative 1 to the n, x to the 2n. So I'm going to integrate the left side with respect to x, and I'm going to integrate the right side with respect to x as well. So the left side turns into arctangent of x plus some constant is equal to, if I integrate the right side, I have the sum from 0 to infinity of negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1. There's a constant on the left side. There's a constant on the right side. I'll rewrite it so both of them combine to make one constant. And I'll put the constant in front of the sigma. So now, if x is equal to 0, the left side turns into the arctangent of 0 is equal to the constant plus all those terms are going to zero out. And the arctangent of 0 is 0. So c is equal to 0, which implies that the function g of x is equal to the sum, as n goes from 0 to infinity, of negative 1 to the n, x to the 2n plus 1, divided by 2n plus 1. Based on this, find the arctangent of 1. If I want the arctangent of 1, I'm going to compute g of 1, which is equal to the sum, as n goes from 0 to infinity, of negative 1 to the n, 1 to the 2n plus 1, divided by 2n plus 1. Which is equal to the sum from 0 to infinity of negative 1 to the n divided by 2n plus 1. On the left side, arctangent of 1 is equal to pi over 4. So pi over 4 is equal to, if n equals 0, the first term is 1. When n is 1, that term is 1 over 3, negative 1 over 3. When n is 2, I have positive 1/5. When n is 3, negative 1 over 7th. If I continue, plus 1 over 9, minus 1 over 11, and so on. If I multiply both sides by 4, pi is equal to 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11, and so on. So pi can be written as an infinite series as well. Use the function f of x equals arctangent of x to approximate the value r sub n is less than or equal to 0.001. So I want the error to be less than 0.001 is what this is saying. Approximate the integral from 0 to 3/4 of arctangent of x squared dx. So this integral is the integral from 0 to 3/4 of the series from 0 to infinity (-1 to the n) x squared to the 2n plus 1 divided by 2n plus 1 dx. So everything's a constant besides anything with an x. So I can rewrite this as the series from 0 to infinity (-1 to the n) times 1 over 2n plus 1. If I distribute this 2, the exponent on x is 4n plus 2. If I integrate x to the 4n plus 2, I get x to the 4n plus 3 divided by 4n plus 3. And I evaluate this at 0 and 3/4. Which is equal to the sum as n goes from 1 to infinity, (-1 to the n), 1 over 2n plus 1 times 1 over 4n plus 3. If I plug in 3/4, 3/4 to the 4n plus 3 minus 0 to the 4n plus 3. Which is equal to the sum as n goes from 0 to infinity, (-1 to the n) times 1 over 2n plus 1 times 4n plus 3 times 3/4 to the 4n plus 3. So when n is 0, the first term is 1/3 times 3/4 cubed. When n is 1, I have minus 1 over 21, 3/4 to the 7. When n is 2, I have plus 177,147 divided by 230,686,720. This value, that fraction, is less than 0.001. 0.001. Since that fraction is less than the approximation that I want, I can approximate this series by its first two terms. And if I combine those first two terms, I get 0.134. So that would be an approximation for the series.